Okay, so for completeness, here's from class 16, or what would have been in class 16 if we had that much time. I'm going to do the MATLAB example 2, or the part of example 2 that is the MATLAB. So what I want to do is write a MATLAB code that's going to solve for the velocity. Now, we don't need to do the Newton-Raphson solution to this. If you remember, for a crank slider, we could solve it directly. It was for a slider crank where we would need to do the Newton-Raphson, where you have the multiple cosines or sines within a solution. You have two equations and two unknowns, but those unknowns happen to be the angles in a slider crank. In a crank slider, we know the input angle, and so we're able actually just to solve that directly. So what I have set up here is just the basic information. We're going to do this for a full rotation, and it's really going to give us sort of an idea of what the numerical differentiation, maybe the difference in the numerical differentiation that's taking place inside of MATLAB compared to what's taking place when we did it in Excel. It's just going to be perhaps an interesting thing to see. It's not earth-shattering or it's not going to reveal a whole lot of things, but it's, I figured for completeness sake. So let's see, I'm trying to look up through my notes and try to find the equations for a crank slider. Now, one thing you're going to be careful of always is the ambiguity issues right here. So we're going to write that theta 3 is going to be equal to, okay, so if I start out, I'll just go the sine, inverse sine of A times the sine of theta 2 minus C. Okay, this needs to be nested up here because that's going to be in the numerator, and all that divided by B. All right, so I've made a string of theta 2's that go for the full 360 right here. Let me clear all this out right here so you could, boom. All right, so if we were to take a look at theta 2 here, double click on it. Where you go, theta 2, double click, there you go. And we want to see where, let's see, I guess we were doing this example for like 60 degrees. And at 60 degrees, I happen to know the radians are 1.042, and so that's going to be in I guess you would say that column 13 as part of this. So coming back to our equation here, what we expect to see in theta 3 then in column 13 is going to be our solution. Right, let's move them over there, and we see that it's 0.4728. Now, if we go back to our Excel, where we had done this, and we take a look and remember 0.4728, yeah, but that was not the configuration. We needed the alternate piece, right? Because there's this ambiguity as to which side the thing was going to go on. Remember that one of them was going to have an angle of where the angle was going to be different, right? So we want the one in the orange, not the one in blue, right? So that ends up being this right here, where we notice we have a negative inside the arc sign, and then we add pi to it, right? So let's make sure that we're doing that. We don't want to forget these things. And so we stick in there, put a negative, and add lowercase pi is what we have. So let's evaluate and then take a look back at these variables, and we see we get the 2.6688. And sure enough, that's the one that we had for the theta 3, the second version of that. So I know I got that right, and now I come back in here, and I want to get my position, right? So the position, this was done in class 8. The position is A times the cosine of theta 2 minus B times the cosine of theta 3. And it looks like I forgot a parentheses after my theta 2 right here. Boom. So let's take a look and see what we would have got. And so that's going to be D now. And that's in 13 over here. Of course, it's just in the wrong spot. 126.83, 126.8. Yeah. Okay. So we got the right thing. So now all that's really done for us is set up the position, but now we can get like omega 3 by taking, well, let's see, do I need, let me cheat and see. Yeah, all right, so here's what I end up getting. Boom, here's what I end up putting in there. I take the diff of 3, divide by the diff of time, and that's going to give me omega 3, and I'm going to do the same thing for my for velocity of b, right? That actually A equals d dot for what we want, but we did it numerically as opposed to using the equation. Now we want to plot the thing. We want to take time because we want to plot versus time. We have to make them equal to each other, and if we note. Okay, so I haven't like actually solved those yet. So we'll go boom, and you see that they're omega 3 and VB are both 216. So we need to drop off time, lop off the end of it, so we have we can plot them versus each other, and then we open up we do a figure, and then we can let's just plot VB. Nope, we need to go time first, right? We need time and V little lowercase VB, and well, I don't need that right there. And if we do this, we should be able to see our figure. We don't know if that's good or it's bad, but it looks kind of like the way it's supposed to. So now I want to try to remember how to do this, and I'm going to export this to Excel. And before I do that, I really should come back into here and get rid of the one that I wrote into there. So back in here, right, we see that what I've done is I've constructed a vertical matrix that's going to look like this now instead, because I use the transpose of these. So if you just take a look, and I just called it V to give it a name, but you can see that we have columns now, and because that's going to fit with our Excel. And then we do a rate matrix into this file right here, which I happen to call MATLAB vel example 2. And when we do, we see over here on the left that the thing came up right here. So let's put them in here, and I haven't tested this out yet. So let's see first if let's see what happens. All right. So I'm going to copy all these columns over with my old Control C, and I don't know. I'm looking at some weirdness taking place there as I look at this. I don't know. Hopefully, we'll see what happens. All right. So I was sneaking a peek at some numbers there. Let me put this over to here, and this is going to be time. And man, here, let me do this again. I go paste. Oh, nope. Let me go back over to here. Sorry. I was just too lazy to highlight everything, so I was going to come back in here and go, like, when I'm inside here, I'm going to get rid of some of yeah, okay. And right here, right, MATLAB, and we notice right away that there is differences. Okay. And so let me move this over. Let me, well, okay, here I can put these in here. I can select data, and I'm going to add and make this the MATLAB, and I'm going to make the time extend all the way down here. Boom. And I don't know why I Okay, Control C right there. Come back up to here because I'm too lazy. Control V. But now we want to plot O instead of M. So I'll go O inside there. And yeah, so it looks like, as far as I can tell, they're pretty darn close. You can't quite see. And there's not enough little symbol-y things here to really give us much of an opportunity to see them. But you could see that they're very close. We would need to very much zoom in to be able to see the differences. But we can take a look at like the percentage differences, right? So we could take and I'm kind of mostly more interested than anything else. Well, first in finding what we would get from the numerical difference right here, because that should really be the closest thing. So let me take, and they actually look pretty far off to me. I wonder if they're shifted. I bet if we zoomed in, we probably would find that they're shifted. But I don't know that for sure. But I bet. And let's take as a, I don't know if we should be doing this actually, the percentage. I don't know if the percentage really tells us as much as maybe just the magnitude difference. That's like 20% off. Of course, that's getting low there, you know, because the percentages are going to look kind of messed up right here. So let's see if let's just actually just take a look at the difference. Maybe that's going to be the most telling thing, is to just see what the difference is. Whoops. Yes. All right. So I think I messed this thing up. No, it's okay. I'll stretch it out a little bit. I don't want it to be a percentage. I want it to be just a number. 69 different. Interesting. Okay. That's good enough. Let's see. Yeah. So you could kind of like take that and take the absolute value of these, maybe, and take the average of this, and then you could kind of give an idea as to what the overall error is going to be, right? By taking it. But this is another example of taking a numerical approach to the thing, and so it's just it's whatever MATLAB is using for their numerical for the diff approach onto the thing. But it's interesting. So that's all I had, and it was 12 minutes of your life that it was worth it, I think. Thank you.